Hello, welcome to another module in this massive open online course. So, in this module let us look at another important application of the principles of linear algebra, and that is in the context of clustering, which is essentially a very important technique or algorithm in machine learning. Okay. So, let us continue our discussion and look at another novel technique, which is essentially clustering, and this is a very important concept in the context of as I said, in the context of machine learning, right. So, clustering is a very important machine learning tool, or what we now call more often as ML. And clustering, essentially what it means is, now what do we mean, okay, I will come to this in a little bit, but now clustering belongs to a class of techniques known as unsupervised this belongs to a class of techniques known as unsupervised learning. What does this notion of unsupervised mean? Unsupervised means you have a large amount of data, and you just have a bunch of data, huge amount of data, and this data is not essentially labeled. No one has essentially labeled or put meaningful tags on these data. So, it is essential that one has to now organize this data so as to say into whatever it is, in a hierarchical fashion, clusters, so on, so as to extract relations and meaningful patterns from this data, right. So, unsupervised learning is essentially learning or machine learning that is performed when there are no, this implies there are no labels on data, right, no labels on data, or data is not labeled. That is another way of saying the same thing. And now clustering naturally means it begins with the notion of a cluster, right. So, naturally a cluster, and all of you must have heard this term cluster, which is essentially, in English it essentially means a group of similar products or a group of similar objects, right. Cluster essentially means a group of similar objects who exhibit some kind of similar characteristics. I mean, that is the intention, that is a cluster is a tightly knit group exhibiting some similar characteristic features, right. So, that is the important aspect here. These exhibit similar characteristics, exhibit similar characteristics, that is essentially. Now, for instance example, you can visualize this as a following diagram. For instance, let us say you have space and then you have the points that are lying as such, and these are, let us say, your points, and then you can see you can extract some kind of meaningful clusters from this. You can form groups of closely related data points, and these are essentially what are these are essentially your clusters, right? I mean closely related points. And clustering is nothing but essentially organizing your data into such clusters, right, groups of objects or data that exhibit similar characteristic, right. So, the clustering algorithm is, which is very important in machine learning, performs this task. So what clustering does is, the clustering algorithm, it organizes unlabeled data remember we said this is unsupervised. So, this organizes unlabeled data into groups containing logically similar points, right, into groups containing, you can say, similar, into groups containing similar points, or you can say objects, into groups containing similar points or objects. And this particular aspect of clustering, this has many applications. It is one of the, it has many applications, such as, what are the applications of clustering? Let us look at some. What are the applications of clustering? For instance, this is applications in data analysis, pattern recognition, recognizing patterns, you can also think of, for instance, such as computer vision, and so on and so forth. For instance, let us take a simple example from this area of computer vision, let us say, or image processing, right. Let us take a simple example from the area of so given an image, one would perhaps like to segment that image into two parts. So, let us say you have a certain person or an animal in that image, you would like to segment the pixels of that image into two clusters, one corresponding to the pixels of the person and the other corresponding to the pixels of the background, alright. So, that is a classical example. So, for instance, let us say you have an image, right, and you have, let us say, my cartoon figure of a person so this is your person and the rest is essentially your background. So, you have the person and you have the background, right. So, you have the background and therefore, the pixels can be grouped into two different clusters. So, the pixels can be grouped pixels can be grouped into two different clusters. And what are these two different clusters? These can be essentially your person, and then you have the background. So, these are the two different clusters. Or for example, you have an image containing, for instance, image of a physical image of a large area containing geographical features such as, for instance, large land body, large areas of land, and then adjoining a water body. So, I would like to probably cluster the pixels into the pixels corresponding to land and water, so on, right. So, you can have an image, or for example, in another example you have an image, and then let us say you have over here you have the water, and over here let us say you have the land. Then you would like to, you take the image and divide that into, cluster the pixels into land and water portion, water region. So, you have the land region and you have the water region, all right. So, essentially what you are doing, this is also termed as, by the way, image segmentation, right. So, you are segmenting the image. So, this basically is also known as image segmentation. Right. What is the meaning of image segmentation? This is essentially segmenting or dividing the image, right, into meaningful visually similar regions, all right. So, meaningful perceptually similar, some regions that have some similar characteristics, for instance, in this case land and water. So, you are taking the regions of the image, dividing the image into meaningfully dividing the image into meaningfully similar regions, right. And for instance, similarly clustering can use to also you can have a large city, and you have, for instance, when studying a disease outbreak, you have clusters, and this is of course shows you directly which parts are, which a pattern of where the disease is growing the fastest. So, you have, for instance, so consider the example of an epidemic or a disease outbreak. Organizing them into clusters of affected clusters or outbreak, that helps us understand how it is evolving, where it is spreading fastest, and there implies basically helps us enable control the spread, right. So, this implies one can study the pattern of spread, plus then followed by this can be followed naturally by the control of such spread. Okay. And clustering can also be used, for instance, to study other, for instance, in finance and marketing you can have applications which can, for instance, you have a consumer database, this can be organized to study spending patterns. Spending patterns in your, it can also be used to study, for instance, the spending patterns in your customer data, so on and so forth. So, clustering has essentially a very large number of applications, and as you will see, because of its rather I would say unsupervised nature, because it does not require labeling, and labeling can sometimes be a problem, especially if you have a large amount of data, and especially because given because as you are going to see, because of the rather simplistic nature of the algorithms, it is very appealing for implementation in practice. In fact, one of the algorithms that is used very frequent in practice in machine learning. Alright. So, let us look at one of the simplest algorithms for clustering. This is known as k-means clustering. Okay. So, the algorithm that we want to look at, this is known as the k-means clustering, which is one of the most popular, this is one of the most popular clustering techniques. This is one of the most popular techniques, and also one of the most, which implies that basically it probably is also one of the most widely embraced and widely used techniques for clustering. And the name is simple, the K essentially denotes the number of clusters, and these are, so K denotes, K equals the number of clusters, and if k equal to 2, then it will be binary clustering and so on, alright. So, k denotes the number of clusters. Okay. Now, we have these data points. How does this k-means algorithm proceed? So, you have this data points x1 bar, x2 bar, xm bar. So, these are your data set, these are vectors, these are your data vectors, let us say these are n dimensional vectors. Okay. Now, typically m is a very large number. M is typically a very large number, and now we wish to organize this. The aim is naturally organize data into, the aim is to organize this into k clusters. Let us say in these k clusters, we denote this k clusters, we have this notion of, so we have a cluster let us say whenever we have a cluster, one way to characterize this cluster is by what is known as a centroid, something that is a central point sort of that captures the location of each cluster in an n-dimensional space. Alright. It might not be simply based on distance, might be based on some notion of distance, right. So, this is something that is closest in some sort of a metric to these different points belonging to the cluster. So, this is what we call as each centroid. So, this cluster can be characterized by this centroid, and each cluster has a centroid for each cluster. So, we will determine the centroid for each cluster. Let us denote these by mu bar 1, mu bar 2, mu bar k. These are essentially the centroids or center of gravity, or you can simply call them as the centers, and so on and so forth. So, centroid, similar to a large object where the centroid is essentially the center of gravity or the center of mass, right. So, that essentially you can think of that as a point where the mass of the object is concentrated. So, the notion is something similar. So, that is a point which sort of best describes this cluster. Okay. So, these are the centroids, and naturally this mu bar I, this is essentially centroid of the ith. This is the centroid of ith cluster. This is the centroid of the ith cluster, and we denote the clusters themselves by C1. Remember, we have k clusters. So, you have k centroids and you have k clusters, right. So, these are the clusters. Okay. So, Ci bar, so mu I bar, this is the centroid of the ith cluster, which essentially what we are denoting this by is, we are denoting this by the set Ci, that is essentially your ith cluster. Okay, and then you have the k clusters. So, this k, not to forget, k equals, once again the k equals k clusters. Okay. Now, the key parameter here is this cluster assignment parameter, which we will denote by this term what we call as alpha I of j. This is essentially your cluster assignment indicator or parameter. And what this, so this alpha I j, as we have alpha I j equal to 1, and what is the role this thing plays? This alpha I j is naturally defined as follows: this alpha I j equal to 1 if x bar j belongs to cluster I equal to 0 else. So, we have alpha 1. So, we will basically have alpha 1 j alpha 1 j alpha 2 j, so on, alpha I j, alpha I plus 1 j, and so on, and then we will have alpha k j, right, one for each cluster for each point j, and this point, if it belongs to cluster I, this will be equal to 1, rest all will be equal to 0, right. So, this implies that point j is assigned to point j, that is x bar j, point j assigned so for a given j only one of the alpha ij's can be non-zero, because each point, remember the fundamental assumption is each point can be assigned only to one cluster. So only one alpha I, so alpha ij for each j can be equal to 0 for only one particular value of I. So alpha I for each j, so if you look at alpha ij for each j ej can equal 1 for only one particular value of I, rest equal to 0. Example, let us take for instance 10 clusters. Example, let us say k equals 10, and then we look at alpha, let us look at j equal to, let us say 2, the point number 2, then we have alpha 1 of 2, alpha 2 of 2, alpha 3 of 2, so on up to alpha 10 of 2, and let us say point number 2 is assigned to cluster 3. This implies this is equal to 1, rest all must be equal to 0, alright. So alpha 3 to alpha 3 equal to 1 and alpha I of j equal to 0 or alpha I of 2 equal to 0 for all I not equal to 2. So this implies x bar 2 is assigned to cluster number assigned this implies x bar 2 is basically assigned to this cluster number 3. So essentially the clustering algorithm is nothing but computing this. So what the clustering algorithm does is essentially computes these alpha ij's. Remember, that's the end of you, that's what you want to have at the end of this algorithm. You want to have for each point you want to have a cluster assignment. So clustering algorithm, right, so that is for all j equal to 1 2 up to m and I equal to 1 2 up to k. That is what your clustering algorithm is essentially giving you. The clustering algorithm is essentially giving you these labels alpha I. So you are now taking the label, and you can think of the cluster as nothing but assigning a label. So you are taking unlabeled data, assigning the label. So that is, so you can think of these also fundamentally as a label, right. So the clustering algorithm, what it is doing is essentially it is taking these chaotic, large amount of chaotic data, clustering them, assigning these labels, all right, and the assignment to a cluster is itself nothing but assignment of a label, all right. So that essentially is basically a high level description of the clustering algorithm. We will specifically look at the clustering algorithm starting with the next module, all right. So let us stop here and we will continue this discussion subsequently. Thank you very much.